This is the fourth of 4 videos for this course. Angular momentum. A spinning top has angular momentum. So does a water pail twirling on a rope, a car rounding a curve, and the Earth in its orbit around the Sun. In 2 and 3 dimensions, the quantum mechanical state for a system can have angular momentum due to the position and momentum of the particle. Even though the quantum mechanical particle has probabilities for its position and momentum, not a deterministic trajectory, and no circular orbits, the system can have angular momentum, and this is called orbital angular momentum. This property is important, interesting, complicated, and mysterious, but beyond this short course. The briefest synopsis is that it turns out that you can choose any axis you wish for describing orbital angular momentum. And when you do a measurement with respect to that axis, the measured orbital angular momentum in that direction will always be quantized in units of h bar, some integer times h bar. Nh bar, n equals 0, plus or minus 1, plus or minus 2. This is a surprising consequence of quantum mechanics and the Schrödinger equation. Recall that earlier I said that the units, the dimensions of h bar, or Planck's constant, energy times time, is also the units of angular momentum. Now, thanks in part to quantized orbital angular momentum, the electrons in atoms have interestingly shaped p, d, and f orbitals, whereas the s orbitals are spherically symmetrical. Let's look at this Wikipedia website. Here are the shapes of some orbitals for which we could take to be for hydrogen. This shape is showing a probability contour. Let's imagine it as the shape in which the probability of finding the electron is 90%. This is the 1s orbital, the 2s orbital. These are both spherically symmetric. We're not going to worry about the blue versus orange coloration. And then these 3 are p orbitals. We could say this is the px orbital, the py orbital, and the pz orbital. Notice that they are not spherically symmetric. Here's a different view of orbitals. 2s, 2p, and then there are d orbitals and also f orbitals. So there's interesting spatial orientation and non-spherical aspects to orbitals, in part due to angular momentum. Here is a different view of orbitals. 1s, 2s, 2p, zxy, 3s, 3p, 3d, and so on. Interesting spatial orbitals. Molecules have sigma and pi bonding orbitals, and we'll look at this Wikipedia website. Here's an illustration of 2p orbitals for adjacent atoms forming a pi bond between the 2 atoms. Here are some atomic orbitals, 1s, 2p, and bonds between 2 atoms, one sigma bond, a different sigma bond, and a pi bond. Here's a different illustration of a pi bond between two adjacent atoms. This light green probability cloud is a pi bond. Two adjacent bonded carbon atoms can have a single bond, sigma, a double bond, sigma and pi, or a triple bond, sigma and two pi bonds. This is the basis of organic chemistry and supports life on Earth. Diatomic nitrogen has a strong triple bond, contributing to the energy released by some high explosives. Intrinsic spin angular momentum. In addition to the orbital angular momentum associated with a spatial wave function, elementary particles and composite particles possess an intrinsic, built-in, internal property called intrinsic spin angular momentum, or spin for short. This is real angular momentum independent of the particle's motion in space, spatial behavior, spatial wave functions, orbital angular momentum, and the potential energy function. This angular momentum is real even when the particle is point-like, such as the electron. It is not really spinning in space. Intrinsic spin is not classical. The electron is not a sphere of charge spinning in space. It is a point-like particle, and yet it has spin angular momentum. Understanding spin is important to properly understand electrons in atomic orbitals, covalent molecular bonds and crystals, ferromagnetic materials, etc. We will not cover spin in any depth in this course, see my other course, but I will introduce a few aspects here. Spin is mathematically simpler than and quite different from spatial wave functions. Spin reveals additional aspects of quantum reality and the essential structure of quantum mechanics. Spin has its own mysteries and challenges for our understanding. Spin is the springboard for understanding technological applications of quantum mechanics, such as quantum computing. Spatial problems and wave mechanics are one aspect of quantum mechanics. Spin is the other aspect. Electrons, protons, neutrons, quarks, and neutrinos, but not photons, are spin 1/2 fermions. If you choose any given direction in space, let's call it the plus z direction, and make a measurement of intrinsic spin angular momentum, you will get one of two values. Either you will get a spin angular momentum of plus h bar over 2, which is called spin up or z plus, parallel to the plus z direction, or you will get a spin angular momentum of minus h bar over 2, which is called spin down or z down or minus z, antiparallel to the plus z direction. It's pretty surprising that this particle intrinsic spin is quantized, the spin will not be zero, and this will be the case no matter the direction in space you choose. This is entirely non-classical behavior. If the way I phrase the spin characteristics make it seem a little obvious or mundane to you, it definitely is not. Ask yourself what results you might get if you measure an electron's spin along the z direction, then you remeasure along the x direction, and then you remeasure along the z direction. In this lecture, we don't have enough information to answer the question, but it's a good question. Spin states for spin 1/2 particles, such as the electron, are called a two-state system, because we can choose two orthonormal basis vectors, and then any spin state's state vector can be represented as some complex linear combination or superposition of the two basis vectors. For a spin 1/2, two-state system, any direction in three-dimensional physical space can be chosen for the first basis vector, but then the second orthogonal basis vector must have the antiparallel direction to the first, not a perpendicular in actual space like Cartesian axes. Opposite spatial directions result in non-overlapping physical basis states for a spin 1/2 particle. This spin state abstract vector space is not physical space. The state space is two-dimensional and can map to directions in three-dimensional space, to having two angles to represent the direction, or to points on the surface of a sphere. The surface of a sphere is a two-dimensional surface. It should probably be surprising that a spin state in one direction, such as x up or y down, can be represented as a complex-valued linear combination of basis vectors z up and z down. But this introductory course will not cover this. Operators that operate on these spin state vectors are 2x2 matrices. Some professors and authors find that spin state vectors and 2x2 operator matrices are easier for students to begin understanding quantum mechanics than starting with Schrödinger's partial differential equation, wave functions, derivatives, and integrals. One good book that takes this approach is Townsend's A Modern Approach to Quantum Mechanics, 2nd edition. Electrons, protons, and neutrons also behave as small magnets. They have a magnetic dipole moment due to their intrinsic spin angular momentum and their electric charge. The neutron is electrically neutral, but its magnetic dipole moment is a residual effect of the three charged quarks that constitute the neutron. The magnetic dipole moment of the electron has 1,000 times higher magnitude than for the proton and neutron due to the electron's much lower mass. Almost always, electrons in atoms, molecules, and crystals are paired up such that the pair contributes zero net spin angular momentum and zero net magnetic moment. Books may say that a spin-up electron pairs with a spin-down electron. Actually, it's more complicated than that, but let's leave that for a more comprehensive course. Magnetic effects by an atom, a molecule, or a solid are mostly due to cases of unpaired electrons. A silver atom has a single unpaired electron, and so has the magnetic moment of a single electron. Perhaps surprisingly, the diatomic oxygen molecule O2, which is present in our atmosphere, normally has two unpaired electrons, and it is paramagnetic. It's attracted to a magnet. Liquid oxygen can be lifted by a strong magnet. Ferromagnetic metals such as iron and nickel get their strong magnetism from a few unpaired electrons in each atom. Multiple particles, tensor product, and entangled states. The total wave function for a state for a system of two or more non-relativistic particles might simply be the product, the tensor product, of the wave functions of each particle individually, in which case both particles are in definite states, typically called a pure state. Or the system state might be a linear combination of multiple such products, in which case the wave function is for the system, not for the particles individually, and this is called an entangled state. In this case, the states of the individual particles are not definite and separate, they are entangled with one another. The states of the individual particles are entangled and probabilistic until the state of one particle or the other is measured, which collapses the system state to a pure state. Shockingly, the two particles with entangled state could be separated by tens or hundreds of kilometers, and state collapse upon measurement of either particle appears to be instantaneous for both particles as far as physics can determine, not limited by the speed of light. But this does not violate Einstein's special theory of relativity. It's a very special case. No delay has ever been found between the collapse of state at one particle and the other. This has been verified many, many times and never contradicted. The spin state for a pair of particles may be an entangled state, a linear combination of tensor products of individual particle spin states. Entangled states are common in atoms and molecules, an important feature of quantum mechanics recognized early by Schrödinger, Einstein, Bohr, and others. Einstein believed that entanglement meant that quantum mechanics was an incomplete theory of physical reality. However, in 1964, an approach was discovered to test whether the physical world obeys quantum mechanics or Einstein's ideas of local realism, and that quantum mechanics is physically incomplete. Every experiment since then has verified that the physical world obeys quantum mechanics. Entangled states are important to modern quantum technologies, such as quantum computing. Identical particles. Any two electrons in the universe are identical. Likewise, any two protons in the universe are identical. Any two neutrons are identical. In quantum mechanics, identical particles are indistinguishable. If the particles interact or are in near proximity, there are no classical particle trajectories by which we can forever keep precise track of each particle. Quantum mechanical states must account for this. We might label electrons as 1, 2, 3 when we express a problem, but they cannot be labeled physically or distinguished from one another. This means that some presumed wave functions that we could write are not physically real, because in those wave functions we can distinguish between identical particles that are in proximity to one another, which is not physically possible in the general case. For a system of multiple non-relativistic fermions, such as electrons, in some proximity, for the system total wave function to represent physical reality, it must be true that exchange of any two identical indistinguishable fermions must cause the total wave function, spatial plus spin, to negate its sign. The total system wave function must be antisymmetric under exchange. This gets complicated beyond what we will cover, but it's important and it has observable consequences. Pauli exclusion principle. Wolfgang Pauli's exclusion principle states, two or more fermions, for example electrons, in a system cannot be found in the same state, the same total state, spatial plus spin. A state can be empty or occupied by a single particle. This is a consequence of the quantum mechanical treatment for identical particles. That exchange of two indistinguishable fermions must negate the sign of the total wave function for the system. In chemistry, we are given, without proof, the Pauli exclusion principle immediately after learning about atomic orbitals as a college freshman or even in high school. In a chemistry course, you might hear the Pauli exclusion principle expressed differently. At most, 2 electrons can occupy a single atomic orbital. Expressed this way, it is implicit and unstated that there are 2 spin states for the 2 spin 1/2 electrons for each atomic orbital spatial wave function. So 1 electron per total wave function, spatial plus spin state. When 2 electrons occupy a single atomic orbital, quote, they must have opposite spin, unquote. Actually, the spin state is a little more complicated because the electrons are indistinguishable. The pair of electrons is in a special entangled spin state called the singlet state, which is antisymmetric for exchange of the particles, which allows the pair of electrons to occupy the same spatial wave function, the same orbital. The singlet state has 0 total spin and 0 net magnetic moment. Almost all of the electrons in your body are paired up in quantum entangled spin singlet states. Your electrons are entangled. You may see articles about quantum computing or other technologies talking about how special quantum entangled states are. And they are, but those articles are talking about 2 particles that are separated from one another, not bound together. Whereas electron pairs in your body are bound together. Modern quantum mechanical technologies. Superposition states and quantum entangled states of separated particles, even separated by kilometers. They can exist, they do exist, and they are important in physics and also to modern quantum mechanical technologies like quantum computing, quantum teleportation of state, quantum communication, quantum encryption, and a future quantum internet. Schrödinger's cat. Schrödinger published his Schrödinger's equation for quantum mechanics, wave mechanics, in 1926. Months later, Max Born published his interpretation that the magnitude squared of the wave function represents the probability density for finding the particle at a location and time, replacing determinism at the atomic scale with probability, which has since been called the Copenhagen interpretation of quantum mechanics. Einstein wrote a letter to Born, a portion of which later became paraphrased as Einstein being convinced that God does not play dice. Niels Bohr later responded to Einstein advising him to stop telling God what to do. In other words, let's see what quantum mechanics says about physical reality, compare it to experiments, and not interject philosophy a priori, or our expectation of what reality is. We should measure reality. After he published his equation, Schrödinger expected that solutions would give deterministic positions of particles, more like a classical wave. Neither Einstein nor Schrödinger were comfortable with the Copenhagen interpretation and giving up determinism at the atomic scale. Concerning the probabilistic interpretation, Schrödinger said, "I don't like it, and I'm sorry I ever had anything to do with it." In order to question and clarify the Copenhagen interpretation, Einstein had an idea for a thought experiment, and Schrödinger published this in 1935 as his Schrödinger's cat thought experiment, which we will now explore. In this thought experiment, Schrödinger places the following items into an opaque box and then closes it for a fixed amount of time. a living healthy cat. One radioactive atom with a decay half-life T1/2. An ideal perfect radiation detector surrounding the radioactive atom. If the atomic nucleus decays, the detector will detect it. A glass vial of poison gas. If the detector detects the radioactive decay, it actuates a hammer that breaks the glass vial, releasing the poison gas, and the cat immediately dies. So here's what we have inside the box. I'm taking this from this website. It was created by author D. Hatfield, and I have not modified it. So there's a radioactive atom, a detector, an actuator, a hammer that can break a glass vial of poison gas, and a living cat which would be dead if the poison gas got released because the radioactive atom decayed. The opaque box remains closed for the half-life of the radioactive nucleus. When the half-life has passed, we open the box. There's a 50% probability that the cat is alive and 50% probability that the cat died. Before we open the box, we would say that either the cat is alive or the cat is dead. But how does quantum mechanics describe the state of the system in the box just prior to our opening the box? If quantum mechanics applies to macroscopic systems and living systems, then the wave function of the system in the box immediately prior to opening the box would be wave function of the system is 1 over square root of 2 times a wave function for the alive cat and a wave function for the dead cat. 1 over square root of 2 because there's 50% probability of the cat being alive or dead at the moment we open the box. This wave function represents the contents of the box as an equal superposition of the cat being alive and the cat being dead at the moment the box will be opened. A superposition of alive and dead prior to measurement, opening the box, which is a different way to say it than saying the cat is either alive or dead. The apparent absurdity of this alive and dead situation is what Schrödinger intended to ridicule by this thought experiment. In his mind, clearly the Copenhagen interpretation of quantum mechanics had led to an obviously absurd description of macroscopic reality, as Schrödinger intended to ridicule. However, the apparent absurdity of the wave function being a superposition of living cat and dead cat did not kill the Copenhagen interpretation or quantum mechanics. 85 years later, the Copenhagen interpretation is still the standard interpretation, and physicists still have no better interpretation for the state of Schrödinger's cat than the alive and dead superposition. This feels incomplete, unsatisfying, and to contradict common sense or at least common language, but it is what it is. Physicists continue to do experiments to determine to what extent quantum mechanical observations can partially look into a closed box without changing the internal state, and new results could come in your lifetime. The Copenhagen interpretation of the quantum mechanical wave function and the probability density is the standard interpretation of quantum mechanics taught in courses and books. There are alternative interpretations which we won't cover, but you can find on this Wikipedia page, Interpretations of Quantum Mechanics. As far as I know, there are no known experiments whose results can rule out some of the alternate interpretations, such as the many worlds interpretation. So no known experiments to prove that the Copenhagen interpretation is the only correct interpretation. Physicists' and chemists' use of quantum mechanics generally follows the shut up and calculate mode. So quantum mechanics is used to predict the results of experimental measurements. Experimental measurements are done, and it's seen whether they agree with the quantum mechanical theory of the problem. Thinking about the interpretations of quantum mechanics may be considered philosophy rather than hard science. However, you're free to make up your own mind on the interpretation and on why quantum reality is the way it is. But all experiments agree on the what of quantum reality, regardless of our difficulty pondering the why. So, even if you ponder the different interpretations of quantum reality, try not to extend that to question whether quantum mechanics correctly predicts quantum reality. It does. This is the final lecture in this short lecture series. Thank you for watching. I hope that you have learned a little about quantum mechanics and this was worth your time. I created this lecture series hoping to reach two audiences: high school students and undergraduates who would likely not take a quantum mechanics course or who wanted a brief introduction, adult continuing education, and senior learners who want a brief introduction. If you enjoyed this course, I ask you to find one friend or acquaintance to recommend this course to, and I appreciate if you would do that. How to learn a little more about quantum mechanics. If you've watched this short lecture series, then you could progress to one or more online course on quantum mechanics if you like. Here are some options. You can watch my longer YouTube lecture series. The playlist is at this link, and the channel is Mongrav. If you want to start learning quantum mechanics from a book and you want to start from spin, from vectors and matrices instead of calculus, try Townsend's A Modern Approach to Quantum Mechanics, 2nd edition. The book Hydrogen, the Essential Element by John S. Rigdon is a pretty accessible combination of a little quantum mechanics and the history of quantum mechanics. And your library can probably get it for you. Now, there are several excellent courses on quantum mechanics available online as MOOCs, most from edX.org, some from Coursera.org. And they're all available to be audited for free. Quantum Mechanics for Everyone, from a Georgetown professor, is very interesting. It addresses some of the mysteries of quantum mechanics, and it does not require calculus. It is not running live currently, but it may be available as an archive. MIT's 804 and 805 series is what their undergraduate physics students learn. Those are excellent courses if you know calculus and you're comfortable with calculus and you're comfortable with differential equations. The professor is excellent. The course material is excellent. MIT's 804 course is restarting on edX on September 17th of 2020, and it is free to audit. There are also good courses from Stanford and Harvard online. Thank you. Good luck with your learning. This is the end of this course.